Thank you for having me and inviting me for this presentation. My understanding is that it is one of the rare presentation about instrumentation. And while preparing it, I had to find a sweet spot to fit what I was going to present between all the incredible facilities that you've been described and that you will be described. And my angle was to try to frame something that would be at least as useful and complementary to what you're going to be presented. So I'm going to, in order to frame my presentation and decide what to talk about, I had the following, let's say, consideration. First of all, most of you are astronomers in the sense that you're exploiting data, and I would not spend too much time on technology, but rather on instrumental concept. Space-based mid-infrared and far-infrared observations are central to many of your topics, and they are well covered by future or planned missions. And in that respect, all these space-based missions have their own research and development programs that are well covered and that I will not talk about. So basically, in the horizon and in the context of PCMI, we've heard that ELT and GWST, the Webb telescope, will be the main horizon, and the instrumental concept are frozen for the next 15 years. So I tried to look into what was not covered by the different instruments and select basically instrumental concepts that are currently quite innovative in the field of infrared instrumentation, and that might be of interest for PCMI. So the goal here, of course, is not to propose an observatory, that's the topic of your workshop, but it's rather to show you new axes of instrumental developments that you might find inspiring, or at least you could contribute to in terms of specification should on-sky demonstration be done. So as was said by Emily before, in the near and near infrared regime, which is basically covering up to 20 microns, what can be seen from the ground, you can observe both gas and dust in absorption emission. You have hydrogen line, you have high silicate oxide nanodiamonds, PAHs, and you have also fine structural lines as well as CO fundamental transitions. And the topics have been already quoted. Exploration of ice line, photodissociation winds, disk evolution, outflow shocks, mineralogy in warm environments. And among all that topics, what I thought would be maybe interesting to you is to describe instrumental developments in two directions. The first one is the direction of a high spectral resolution. By high spectral resolution, I mean instruments that might allow to pass the 100,000 spectral resolution limit, which is basically going down to a fraction of kilometer per second. And the second one is, of course, going towards higher angular resolution, even higher than what was presented for METIS. So basically, my presentation is divided in two main sections. The first one where I will describe three innovative spectrometer concepts. I know you're all physicists, so it will remind you maybe your optics lessons, and you will see that there are probably interesting stuff to get from that. And then I will discuss the future of infrared interferometry beyond the LTI, which might also be of interest, as we've seen just before with Emily. So I've selected three concepts, and the first ones are related to high resolution spectroscopy. And there are many facilities that have tried to reach the 50, 80, 100,000 resolution. And this is done basically with classical Echelle spectrographs, which are expensive and bulky, and for example, not necessarily compatible with space-based mission, and Fourier transform spectrometer. And one of the interesting developments in the recent years interestingly, it's not a recent development in the field of physics, but in astronomy. It's the replacement, and here you can see, I don't know if you can see my mouse.
Yes, we see it.
So you can see that in the new concept of high resolution spectrometers, the échelle, the grating, has been replaced by a component which is called a virtually image phased array. And this has the interesting capability of basically being based on the Fabry-Perot effect that allows from an injected slit to develop and generate multiple images that interfere in order to provide the grating effect, the dispersion effect. And in comparison to classical spectrometers, it has a much higher angular dispersion, much higher throughput, and low polarization sensitivity, which allows to consider quite easily spectrometers with resolution of 200, 300,000 and even more, keeping a very compact design. So there is currently an experiment between IPAG and Palomar, Caltech, which aims at demonstrating that this concept is working in the context of high dispersion coronagraphy that combines coronagraphy and high dispersion light of a planetary signal in order to disentangle it from the stellar light. And you can see here, first of all, the demonstration of 100,000. It was basically it's a 20,000 euro experiment showing that you can build quite easily a high resolution spectrometer. This is 100,000 spectrogram of the sun compared to the reference spectrum. And on the bottom, you can see a very compact 100,000 spectrometer, which is basically 50 centimeter wide instrument, which is called HTC for high dispersion coronagraphy, and that will go to Caltech. And when you look carefully at the materials, you can clearly see that this concept could be extrapolated to higher wavelengths, because it's basically the key component is this VPA Fabry-Perot cavity, which is easier to make in the mid-infrared, at least in terms of surface quality. The second trend that is developing mostly in planetary atmosphere science, but it's basically benefiting from the incredible progresses in technologies in the mid-infrared, in particular the quantum cascade technologies. For those working in the terahertz, this is not news, but in the mid-infrared, this is relatively recent, and where you can develop heterodyne interferometry or heterodyne spectroscopy at low cost using newly developed mid-infrared lasers and high bandwidth quantum cascade detectors. And this technology is currently being experimented in Hawaii with a spectrometer that has been designed to target specific lines from the ground and has specific local oscillator for each line, and it allows to reach a million of spectral resolution. And of course, this is done on planetary atmosphere. This is relatively bright, but this is on a small telescope. And all these technology have to be considered in the framework of the giant telescopes, for example, the ELT, and also in the context of ever improving sensitivities of detection technologies. And the last concept I would like to highlight is an interesting combination of Fabry-Perot and direct imaging, which I've illustrated here. So I'm going to try to focus on the center image, where you have a field of view that is basically divided into a sub field of view, and you have an image per lenslet. But for each of the lenslet, you have a Fabry-Perot effect that allows you to encode the lines and decide specifically of which lines you're interested in order to put the imprint on the image. So in the end, what you get is that you have an image for which you can determine the line presence at each pixel with a high accuracy. Of course, it's not a broadband spectrometer effect, but it allows to select by design which lines you're interested in and provide you this kind of wide field line selection capability. So these are the three spectrometer developments that are currently quite active in the field of infrared observations, and I think deserve to be examined in the context of PCMI scientific interests. So the next and the last second part are the development of technology for next generation mid-infrared interferometers. And here I would like to highlight the initiative, which is called the Planet Formation Imager Initiative, which was launched a few years ago, maybe 2015, 2016, with the aim of projecting ourselves in the future and thinking about what would be a post-VLTI facility. And the main topic of interest that basically forced the design was the studies of planet formation at very high angular resolution, with the goal of characterizing young exoplanet up to Taurus, mapping disk winds and photoevaporations within 5 astronomical units, mapping the chemical and gas components within these 10 or 5 astronomical units, and even reaching angular resolution sufficient to resolve both spatially and kinematically circumplanetary disks, again within 10 astronomical units of the central star. So this initiative was supported by a number of working groups. The PI is John Monnier and the project scientist Stefan Kraus. And there's been quite a number of work in order to try to define the science case, of course, better, but also to define an architecture of for this future facility, which is basically maybe in a simplified way a sort of ALMA facility, but working in the mid-infrared with maybe less telescopes. So here you can see that the science working group went through the simulation of how protoplanetary disks, forming planet disks, would look like different wavelengths. And this allowed to define basically broadly 2 domains of operation of this interferometer, the 3 to 5 micron domain that would target basically young exoplanets, and the dust and gas imaging that would target the 5 to 13 micron regions. So in that context, there were several simulations were done, and you have here an example of a Jupiter-like planet carving a gap inside its disk, and a reconstitution of what could be retrieved with a 12 meter telescope PFI-like facility in 100 hours. And you have here roughly the dimensions, the number of telescopes, and the fact that you're basically going to kilometric baseline now, compared to the basically hectometric baseline that you have currently with the VLTI. So there are different challenges, of course, with that, and the comparison, of course, that will appear immediately is the comparison with ALMA, which has an incomparable image complexity, dynamical range, spectral resolution, and angular resolution. And this is basically the source of inspiration for infrared interferometry, is really to go as much as possible in the direction of millimetric imaging. So there are currently 2 architectures that are contemplated. The first one is called the direct interferometric architecture, which basically would build on VLTI technology. It is intrinsically more sensitive, but it would require to build an infrastructure at the kilometric scale that would include all the tunnels to carry actually the light from the telescope to recombine. And the other one is getting inspiration from what is done in the millimeter and trying to develop heterodyne technologies in the mid-infrared in order to allow a much complex infrastructure with much more telescopes, but a much lightweight way of transporting the information. And of course, heterodyne would allow to have much narrow band, much lower band passes. So the current thought process on the PFI is on the heterodyne aspect is really to think about what could be a purely fiber-linked facility that would basically just would need the telescopes and some heterodyne detection scheme and photonics transportation that would allow to correlate the signals, or a typical ALMA-like correlator, but that would be much more complex. So this is one of the architecture that is currently contemplated that would allow them to focus mostly on building the telescopes, and then the infrastructure would be much lighter. So we are not starting from nowhere, because this is something that Charles Townes, a Nobel Prize in Physics for inventing the laser, was very fond of. This is something he spent a lot of energy towards the end of his life, and he actually demonstrated that heterodyne interferometry at 10 microns could work on the by building the infrared space interferometer on Mount Wilson. So this is basically, this paved the way for the technology, and since then, as I mentioned earlier, for spectroscopy, heterodyne technologies in the mid-infrared have considerably evolved. So the challenges ahead for a future facility that would target the infrared, and in particular the lines and structures I've mentioned before that would be of interest for PCMI, are the development of low-cost telescope technologies, adaptive optics, fiber links, co-phasing and delay lines. And in the case of heterodynes, the challenges are high bandwidth detector, mid-infrared frequency comb, low cost dispersers, and phase lock of a kilometric baseline, as well as a correlator that would have a quite significant different architecture with respect to ALMA, for example, because of the different spectral bandwidth of the observer. So just a few mentions of technology. This is we mentioned Matisse earlier. This is a MIDI spectrum. Matisse has basically the same spectral coverage. So if you're doing, you can see, so in terms of frequency, this is a very wide band pass. So there's you have to, in order to do that in the mid-infrared, in heterodyne, you have to really define and design technologies that allows to increase the bandwidth using these new quantum cascade detectors that are currently developed, for example, in Paris or in Cologne, and also using frequency comms. So these are currently active topics of research, not necessarily in astronomy, but that could benefit astronomy. The second interesting advance that has direct impact on the perspective of having a kilometric baseline interferometer is the recent demonstration that you could lock a local oscillator through a fiber link, a mid-infrared local oscillator at 40-kilometer distance, which is way beyond what is needed for a PFI-like infrastructure. So these are two examples, and I could mention, but I don't think I have time, I could mention other ones showing that there are technologies and advances in the right direction for astronomical interferometry in the infrared. And last, I would like to mention also something that I currently don't know the status, but just to show you that there are some interesting ideas, and this is developed in Germany by the German Space Agency, and we are here going down to lower frequencies, but just to know that there are initiatives currently to study infrared interferometric missions in space. You can see here that we are exactly in a regime, so in a regime between 50 to 300 microns. That could be of interest for high angular resolution studies of molecules. This is probably currently at the level of technological demonstration, but it's interesting to know that it is under consideration, and that we could think about extending it towards shorter wavelengths. So I will wrap up here and just repeat that there are lots of technological advances in the near and mid-infrared in the context of the different space missions, and I have not covered them. There are interesting development in detections, in cryogenic, in photonics. The current prospect for PCMI science is probably linked to the GWST and ELT, like Emily said. So basically, the contribution of PCMI or the interest of PCMI in the next decade for new instrumentation might be low, but at the same time, there is certainly an interest in collaborating with people working on high spectral resolution or high angular resolution in order to inject knowledge and allow to properly dimension future spectrometers or future interferometers. And I think that's where the overlap could be interesting. So two instrumental concepts have been presented to push spectral resolution beyond 100,000. The Planet Formation Imager initiative has been presented. It's not an actual facility, but it's a good driver for instrumental research. And once again, it would be interesting to get PCMI science case input in order to validate, for example, the architecture. And I think I will stop there.
Thank you, Jean-Philippe, for this very interesting talk. There are a couple of questions. Martina?
Yes, hello. I'm coming from the millimeter terahertz domain. What mixers are you using in the heterodyne mid-infrared spectrometer?
So in the heterodyne mid-infrared spectrometer here, we are using a beam splitter, a typical beam splitter like in optics, and at the output of that you have a quantum cascade detector. So basically, what you get at the output is the beating the interference between the local oscillator and the incoming light, and this is encoding into an intermediate frequency signal through a detection in a quantum cascade photodiode.
Okay, I'll look at that. I know about quantum cascade lasers, but not the detectors yet.
Yeah.
Thank you.
Claudia?
Hi, yes, I also come from the sub-millimeter community, and I have two questions. One is probably very silly, which is, would it be possible, feasible, or even interesting to test this mid-infrared heterodyne technology on existing sub-millimeter facilities, either single dish or interferometers?
Well, I would say the main problem is the quality of the dishes. So if you're going down to let's say 10 micron with a dish that is designed for millimetry, you will have a very bad. Well, first of all, the reflectivity would probably be not very good, and the surface quality would not be very good. And in this concept, what is very important is to have a good overlap between the local oscillator and the incoming signal. So on the detection part, I would say that it's probably too early to go to single dish. Although I would be very interested to know what is the quality.
Current ALMA, for example, I think they have a surface accuracy of 20 microns. And which is more or less this, maybe a little bit better Apex, maybe down to 10 microns. But I was thinking maybe with some particular coating or
Yes.
In the future when some of these facilities will be outdated, so maybe they can be used to test.
Yes,
anyway, this was just a curiosity.
But we have the intention of trying to testing on Sky. For the moment, the idea is to do that at VLTI. But of course, a facility with a bigger antennas would be interesting in terms of collecting area.
And the other question I have is whether the baselines are stable in this kind of mid-infrared heterodynes, and if the bandwidth is large enough and stable enough to allow broad line observations from extragalactic sources.
Yes, they are quite stable. So in terms of extragalactic observations, the experience with VLTI has been limited in the sense that the sensitivity of the previous instrument was limited by the fluctuations of the atmosphere, which are very fast in the infrared. So I would say that it's not the baseline, but rather the ability to correct for atmospheric fluctuations which happen at timescales of 100 milliseconds. That is the key to extragalactic science.
Indeed, in some millimeter, we use beam switching.
Yeah, so we unfortunately we don't have quasars in the mid-infrared, but there is currently a very interesting development by the Max Planck in Garching, which is an upgrade of the gravity instrument at VLTI that should allow to have an off-axis target. So it's basically similar to beam switching, but it's basically observing two objects at the same time in order to stabilize the fringes.
Thanks.
Thank you.
You've been speaking about trying to define science case, but you didn't speak about potential sensitivity you could reach. In order to work science case, it would be interesting to have some numbers on order of magnitudes of what we can expect of sensitivity at the resolving power of 1 million.
So I haven't done the computation at 1 million, but we looked at one of the things we are interested is eventually to have an instrument at VLTI that would be devoted to the neon line. So we were targeting 1,000, and the sensitivity at the moment we can get is about 100 millijanskis in I don't remember 2-hour integration time.
Okay.
So basically the brightest young stars.
Yeah, no. Yeah, but it would be interesting to have for your PFI. It would be interesting, for instance, to have some numbers also. What we could achieve with such a large collecting area.
Yes, that's what we're missing at the moment.
Any other questions? No. Thank you very much.